Hello and welcome to this presentation on hardware vulnerability assessment. What we're going to be looking at today is the process and the process model associated with how do you perform a hardware vulnerability assessment. Our key learning outcomes are to understand the hardware hacking process model and its key elements, to understand the role of stakeholders, as stakeholders play a critical role in this process. We also need to understand the legislation and how they relate to a hardware vulnerability assessment. After all of our actions have to be performed in a legal, moral and ethical framework. And also to understand the role of open source intelligence, attack surface analysis and exploitation within the hardware hacking process, as these are the key elements and the key processes that we're going to perform. So let's crack on and look at the process model in a little bit more detail. So let's look at the process model in a bit more detail. At the heart of the process model, we have the stakeholder. The stakeholder defines the reason for the test, i.e. the requirements, and the success criteria for the test, i.e. how they're going to evaluate the report. The actions that we're going to perform in the test are attack surface analysis, open source intelligence analysis, and exploitation. The stakeholder is at the heart of the test. They define the aims and objectives of the test, the reason for the test. They define the scope of the test, what's in bounds and what's out of bounds. What are we allowed to do? What are we not allowed to do? Are we allowed to be destructive on the test? If we're testing hardware, are we allowed to destroy the hardware as part of the test? They also define the timescales and costs. How long should the test take? In addition, they'll also help us identify other key stakeholders. This could be stakeholders within the organisation, such as designers. It could be regulatory requirements, such as the regulatory framework within which the hardware is going to operate. Take, for example, medical IoT and medical embedded systems. They have to comply with medical regulatory requirements. They're also going to define a list of deliverables that we have to do and a capability statement. The capability statement is because when performing a test, we're functioning as a specific threat actor with a specific set of capabilities, and we are in effect simulating that threat actor and simulating those capabilities. They define the target of the test and also the regulatory requirements. They also help us to define the simulation of the threat actor or threat agent that they want us to test as. i.e., are we talking about espionage, somebody trying to get intellectual property? Are we talking about crime, perhaps somebody trying to engage in extortion? Or are we talking about an insider threat? In terms of the report, they talk about the acceptance criteria. What are they looking for in the report? Are they looking for us to write War and Peace, a 300-page report? Or are they looking for a more succinct, perhaps a PowerPoint presentation? Perhaps a mixture of the two? What we're really doing when we conduct a hardware vulnerability assessment is we are simulating a threat actor or set of threat actors. While each threat actor is unique and will have its own motivation, they will have a set of core capabilities. Some of those capabilities may be unique, but some of them will be in common. The threat actors that we're concerned with are hacktivism, crime, insider, espionage, terrorism and warfare. And the two that we're particularly interested in are crime and espionage. Crime is where a group will seek to extract information, potentially discover a vulnerability, and use it to blackmail an organisation in order to achieve financial or political influence. Espionage, we're talking about national state actors conducting computer intrusions to steal sensitive information. This can also include commercial organisations looking to steal your intellectual property. You see, when an organisation produces an embedded device, an IoT device, what they're embedding in that device is their intellectual property. And that intellectual property is worth money, and people may seek to steal it. And that's really what a hardware vulnerability assessment is all about, is it's gauging the level of difficulty associated with retrieving that information. And so based upon the risk appetite of the stakeholders, we'll determine the nature of the threat and the threat actors that we are simulating. The goal of tamper resistance is to stop somebody tampering with it. And so as part of a test, it could be that we are evaluating the tamper resistant strategy and techniques that have been deployed on the device to see how difficult it is for somebody to extract intellectual property. And we can define these down into 4 areas: resistance, evidence, detection and response. Resistance is that it should be difficult to tamper with it. This can involve, for example, unique screw types. Evidence says that any tampering with the device should clearly be evidence on the device. Detection allows the device to be aware of tampering and can include things like magnetic switches, pressure contacts, and radiation sensors. Such as, for example, we've seen X-ray dyes used on integrated circuits so that when people try to X-ray those integrated circuits in order to extract the circuit design, the X-ray dyes themselves crack, rendering the integrated circuit useless. And this cracking process we call tamper resistance response, allowing the device to respond to an attack when it's detected. Any actions that we perform must be performed within a legal, moral and ethical framework, and so there are key pieces of legislation. Now here I'm going to focus on the UK legislation, but you should be able to map this into your own legislation in the countries where you're coming from. In the UK, we have the Computer Misuse Act, which talks about computer hacking and the modification of data. We talk about data protection, in particular GDPR. This is the protection of personal data. We also have intellectual property and copyright law, and this is primarily what we're concerned with when we're doing a hardware test. Can we extract the intellectual property of the design? Can we reverse engineer? Can we modify that? What are the legal frameworks within which we can do that? And finally, contract law and the Sales of Goods Act. We're going to be offering our services. Somebody's going to be paying for it. That has to be done within a legal framework. The other key aspect to remember when agreeing a hardware test, and this is perhaps the most important, is does the person who is instructing us to do the test actually have the permission, the authorization to instruct us, or do they not, in which case we could be breaking the law. So, the key pieces of legislation that we're concerned with the UK are the Computer Misuse Act. Now, the Computer Misuse Act is talking about the modification of data, the unauthorised modification of data. And in order to be guilty of an offence under the Computer Misuse Act, you have to have what's called the criminal mind. This means you have to know at the time that you are committing the act that the act you are committing is a criminal offence. We have data protection law in the UK, and this talks about the protection of personal data and how personal data should be protected. And in particular, the organisation should take all reasonable technical measures to ensure that personal data is protected. We have copyright law. This comes down to the Copyright Designs and Patents Act and the Copyright Amendment Act dealing with computer software. And this is basically defining computer software as intellectual property. And so we need to be careful that the intellectual property that we are accessing, we have permission to access. We also have the Sales of Goods Act, and this basically defines the framework within which we're going to do the test, i.e. the contract. We are going to have a contract with the stakeholders giving us permission to do the test, and there's a framework around that for things like payment and stuff like that. So, what is the process model? The process model is the stakeholder defining requirements for us and defining acceptance criteria for a report. Attack surface analysis, open source analysis and exploitation, and also the system interface itself. We're going to be considering the hardware device from a holistic perspective. That is, we're not just going to be focusing on the electronics, but we're going to be focusing on things like the human interface of the electronics and treating it as a whole device. The system interface, we're talking about things like human-machine interface, buttons, LEDs, sensors, screens. We're also talking about things like smart cards. Often these devices, embedded devices, IoT devices, use smart cards as a file system, and therefore intellectual property, i.e. the software, can be on the smart system, those smart cards. And so all I need to do is to remove the smart card in order to access the system. The attack surface analysis, we're talking about things like network access points, Cat5 cables, Wi-Fi, Internet of Things. The Internet of Things starts with the word Internet. That by definition implies a network. That network by definition implies some form of communication with other devices. That communication is going to take place over an infrastructure and make use of a protocol. So it could be we're talking about TCP/IP. It could be we're talking about Zigbee or RFID. But there's going to be communication, and we need to be able to identify this communication, sense it in the world within which the IoT embedded device is operating, and perhaps modify it and replay it. This can lead us on to talk about port scanning and banner grabbing and OS fingerprinting. Remember, most embedded devices today are either running specific software designed for the device or are running an application on top of an operating system. If it's running an application on top of an operating system, that operating system is going to be identifiable, and we can identify the ports and services that it's using. Many embedded systems today make use of web servers and web engines as a way of doing simple configuration. They also make use of SNMP, Simple Network Management Protocol, as a way of allowing you, the user, to configure the device. And we can also do network sniffing and infrastructure simulation. So network sniffing is sniffing the infrastructure, the ether if you will, that the device is communicating over. And if it's communicating to servers, perhaps simulating that server and that infrastructure to see if there's a way we can inject data into the device. For example, if it's downloading updates, are those updates digitally signed? Is it using a secure socket layer in order to communicate with the update server? Is there some form of crypto keys? Or is it simply making a HTTP GET request, downloading some software and executing that software? In which case we could create the infrastructure and exploit that vulnerability of the HTTP GET request. Also, we've got the attack surface analysis. This is actually looking at the physical device itself to see what's there. And this involves things like the identification of power and ground signals, looking at potential vulnerabilities there, identification of key components such as integrated circuits, identification of debug and access ports such as VGA, RF, Cat5 we've talked about, USB 2 and USB 3, UART, SPI, JTAG and other buses such as CAN buses and things like that. The idea of PCB analysis would result in a conceptual design of the PCB, i.e. what we're doing is we're going from a physical process, a physical design, into a logical process and a logical design. And this logical design will allow us to analyse the device in greater detail. But in order to do that, we need to be able to analyse the physical device, i.e. analyse the PCB, and identify things like debug ports, integrated circuits. The key part of identifying integrated circuits is that those integrated circuits will have pins that are communicating to the outside world. And if we can download the data sheets for those integrated circuits, we can identify the pins. And when we identify the pins, we can start attacking the integrated circuits to see what it can do. So here we can see an example of a PCB analysis. Here you can see we've got a bus connector in terms of serial, looks like a serial connector to me. We've got some power plugs, we've got some integrated circuits, flash memory, we've got what looks like a CPU, we've got an Ethernet controller, and you'll see we've got tracers running between those devices. So we can see we've got a Siemens integrated controller talking to SPI flash memory. Chances are that SPI flash memory is going to contain the firmware. We've got some NAND flash memory. We could look at that. We've got a power circuit. We've got a bus connector, VGA. What's it doing? What's the VGA giving us? We've got an Ethernet connector. What's coming out of the Ethernet when we switch it on? All of this is allowing us to construct a conceptual design of the device. And that conceptual design of the device will help us in the logical analysis, i.e. the attack surface analysis, so we can identify how we want to attack it. One of the ways that we can analyse a PCB is to perform X-ray analysis. Now the goal of X-ray analysis primarily is to allow us to identify the pins and the flow of pins, what we call tracks, from one integrated circuit to the next. The reason for this is we're going to use data sheets on the PCB to identify what the pins mean. And then, via looking at the tracks of where those pins connect to other pins, we're going to be able to build up a logical design of what's actually going on. Now, all of this is underpinned by open source intelligence. I've talked already about getting data sheets and using analysis of the PCB to identify integrated circuits. and then using the make and the model of the integrated circuit to download a datasheet. That's open source intelligence, and it's using it to basically help us identify the attack surface. So what we're looking for is user documentation provided with the product, i.e. the integrated circuit. Typically that user documentation would be a datasheet. It could be user documentation provided with the device itself. The use of search engines, looking at product review sites. Often product review sites will perform a preliminary hardware assessment in terms of looking at the internals and telling us what the integrated circuits are. Product vendor site and supplier sites. This is looking at the site itself supporting the product that we're testing and the vendors associated with it, and to see what other information they're giving out. Data sheets I've talked about. Books and other online educational material. Perhaps the products that you're dealing with in terms of integrated circuits or the device itself has been analysed elsewhere. Perhaps an integrated circuit, a controller chip for example, these are typically ARM chips, but perhaps they've been analysed somewhere else. You can also look at regulatory and patent sites and see what's been filed in terms of the protection strategies and methods. And finally, looking at PCB design software. These software packages often contain data about the integrated circuits that we want to analyse. So open source intelligence is critical to this process. In fact, it's very difficult doing a hardware vulnerability assessment exercise without good open source intelligence. I'm going to run through some sources now to help you in terms of open source intelligence. So anything that communicates and is sold in America has to be registered with the Federal Communications Commission, and we can search that website and they will often have teardowns for us of products and manufacturers and things like that. Sometimes shops, particularly if you're analysing phones, such as the Phone Scoop shop, is a really useful source of intelligence. Also, analysing chips and integrated circuits such as findchips.com is a good site for looking at data sheets and extracting data sheets. There are others. We can also look at the manufacturers of the integrated circuits itself, Intel, Micron, Toshiba, Winbond, etc. These sites will contain data sheets and may contain product information allowing us. Of course, we shouldn't forget search engines such as Google, Yahoo, Bing and Ecosia. And here I want to have a little shout out for Ecosia and saying for those of you that want to save the planet, you should really be using Ecosia. They plant trees. We've got security sites such as CERT, UK CERT and Process Control CERT, which publish advisories. And also we've got patent information related to the product. All of these are good open source intelligence tools that we can use. Now, one of the things that's really important when we do a test is that first and foremost we remember we are scientists. The tests have to be structured, they have to be calibrated. In order to do that, we need to understand the difference between a test that succeeds and a test that fails. And that is for all of the tests that we do, we need to understand what the success criteria looks like. If we're measuring voltage, for example, have we calibrated our voltmeter? If our voltmeter is telling us it's 5 volts, is it really 5 volts? So calibration of tools and techniques is critical to a test and should always be done prior to the commencement of a test. This can involve us having test boards which are in known good states. For example, test boards for UART, serial programming, JTAG, USB, etc. They allow us to calibrate our tools. So for example, if I'm looking for a UART signal, and my tool for identifying a UART signal, I need to know that that tool is working correctly. A calibration board allows me to do that. So when I run a test on the target of evaluation, i.e. the board I'm testing, I'm going to know whether that success is a pass or a failure. Finally, exploitation. This is where we start to get our hands dirty. So we've got the device. We've done some attack surface analysis to identify components. We've done some open source intelligence to help us identify pins and things like that. And now what we're doing is we're going to start exploiting things. And this can involve the use of oscilloscopes and logical analyzers to help us analyze protocols to identify firmware and host operating systems. It can involve us sniffing data on RFIDs, wireless, TCP/IP and things like that. It can involve us connecting to debug ports such as UART, SPI, I2C and JTAG, and I'm going to deal with those in a later presentation in terms of what the actual protocols are. But for now, just suffice to say, these are the debug protocols that we want to be able to identify that are going to give us low-level access to the devices. It could be that we're talking about using software and chip-based debuggers to actually debug the device. Remember, when we write software, whether it's Java, Python, C, etc., we use debuggers to debug our software. Writing software for embedded systems and designing embedded systems is no different. We still need debuggers to help us debug our software and debug our hardware. And those debuggers can be used as part of our exploitation process. And finally, we're looking at chip-off attacks. This is where we physically remove the integrated circuit from the device and put it into a chip reader. So for example, it could be flash memory. You take the flash memory off the device and you put it into a chip reader in order to make it easier. Other types of techniques we can have for exploitation are things like fuzzing. For example, if we're using embedded hardware and embedded software and it's not written on top of the operating system, and that embedded hardware and software is making use of USB, or perhaps we can look at fuzzing the USB to see if there's a buffer overflow in there. Brute forcing usernames and passwords. Remember, many embedded devices have default passwords built into them. Think about your home ADSL router. This is a device that has a built-in password. Think about SCADA and industrial process control systems. These are devices that are going to be out there in the wild for many, many years, and chances are have default passwords. And finally, we can look at if we can extract the firmware or the software, reverse engineering it to identify key components. Perhaps a password is embedded in software, and if we can extract that password, we can access the device. Perhaps there's a vulnerability in the firmware, and we can use simulation tools to help us identify the vulnerability. The key point to remember in all of this when we're doing a hardware vulnerability assessment is that the attack surface, the system interface, open source analysis and exploitation are all iterative in nature. For example, if I start with attack surface analysis, I may identify a UART pin, so I can move straight to exploitation in terms of validating that UART pin and looking and seeing what's going on. It could be I go from attack surface analysis to say, yes, it has a system interface, some buttons, a graphical user interface perhaps on it. I can look at that. It could be that I go from attack surface analysis to analyse the PCB in terms of open source analysis that may lead me to go back to further attack source analysis in terms of identifying pins and then move to exploitation. The real point I'm making here is that it's not like a waterfall model. When we do software design, we can do design, but we can do specification, design, implementation, and testing. And we tend to treat it as linear in nature. This isn't linear in nature. It's cyclical in nature. And from any point, we can go to any other point. And this is why it really differs from software testing and software development, in that from any point, we can go to any other point. And from any point, we can move back to where we started from. And ultimately, this should lead into our report and our test results. Well, I hope you've enjoyed this presentation on hardware vulnerability assessment. What I've tried to do is to give you a flavour of some of the key components in the process model of how you construct and execute a vulnerability test.